The topic for today is homomorphisms. A homomorphism is a function very similar to an isomorphism, as we'll see. The basic idea is that a homomorphism from a group G star to a group H circle times is a function from G to H, just like an isomorphism would be a function from G to H. And the function has to preserve the group operations, just like an isomorphism does. So the difference is that a homomorphism is not required to be one-to-one or onto H like an isomorphism is. Okay, here's the definition. We assume we have two groups, G star and H circle times. And then a function from G into H is a homomorphism from G star into H circle times. Or more frequently, we just say a homomorphism from G to H if for all A and B and G, f of A star B equals f of A times f of B. So this is the equation that says that f preserves the group operations. It's exactly the equation that an isomorphism has to satisfy. We frequently write this as f of AB equals f of A, f of B. In fact, our book always does that. But if this happens, you've got to realize that the A times B on the left-hand side means that we're combining A and B using the operation star from G. And on the right-hand side, we're combining f of A and f of B using the operation from H. So at least for this set of slides, we won't be doing this. Okay, and one thing to note is that a homomorphism from G to H does not have to be one-to-one, nor does it have to be on to H, like an isomorphism would have to be. In most of our examples, though, the functions that we look at will be on to the second group H. Okay, a couple of easy facts. First of all, an isomorphism is always a homomorphism, right? An isomorphism fulfills the requirements for being a homomorphism and more, has to be one-to-one and onto. Second easy fact, if you have any two groups, G star and H circle times, there is a homomorphism from the first group to the second. It's the function defined by f of A equals the identity in H. So f is the function that takes every element of the group G and matches it with the identity of the group H. This is a homomorphism, usually called the trivial homomorphism. Okay, let's try this example. So we're going to define a function from U15 to U5. The formula for defining f is that f of A is A mod 5. So this will take elements of U15 and give you elements of U5. And we're planning on giving a proof that f is a homomorphism. Okay, first, I just wanted to remind you of a couple of facts which will get pretty frequent use in this argument. First of all, the inserting or deleting multiples of M lemma. Right, this tool that we used quite a bit earlier in the course that says that if you have a multiple of M inside a mod M, it can be eliminated. You can delete multiples of M inside a mod M and also insert multiples of m. And the second reminder is the eliminating mod m lemma. So x mod m we know is always equal to x plus k times m for some integer k. This allows us to eliminate x mod m in expressions involving it. Okay, so we're working with the function f from u15 into u5, defined by f of a as a mod 5. Just a reminder of the function that we're proving is a homomorphism. And what we have to argue for is the homomorphism equation that f of a times sub 15b is f of a times sub 5 f of b. Right, times sub 15 is the operation in U15, and times sub 5 is the operation in U5. Okay, this, if we were going to follow the book's convention, we could write this equation as f of ab is f of a times f of b, but then we'd have to remember that this a times b means times sub 15, and this f of a times f of b means times sub 5. Okay, so we are showing that f of a times sub 15b is f of a times sub 5 f of b. We'll start with the left-hand side and try to simplify as much as possible. A times sub 15b is equal to, using the definition of times sub 15, right? A times sub 15b is by definition a times b mod 15. And now we use the eliminating mod m lemma. A times b mod 15 is a times b plus some multiple of 15, 15s in our proof. Now the definition of f. F of a number is that number mod 5. So we're using the definition of f. We get a times b plus 15s all mod 5. Okay, just rewrite the 15 times s as 5 times 3s, just to emphasize that this is a multiple of 5. And then by the inserting and deleting multiples of m lemma, we can delete the 5 times 3s. A times b mod 5. This is probably as simple as we're going to get the left-hand side. Okay, here's just a review of where we are. We're showing that the homomorphism equation is true, and we've calculated the left-hand side, and we have gotten a times b mod 5. Now we work on the right-hand side, f of a times sub 5 f of b. Okay, using the definition of times sub 5, when you're multiplying two things times sub 5, you multiply them and then take the answer mod 5. So this will be f of a times f of b, the product mod 5. Using the definition of f of a is a mod 5 according to the definition of f. F of b is b mod 5 according to the definition of f. So we make those two replacements. We now use the eliminating mod m lemma. A mod 5 can be replaced by a plus some multiple of 5. We called the multiple 5s here. B mod 5 can be replaced by b plus some multiple of 5. b plus 5t. We do the multiplication. Now I've done a little bit of algebra here. I've multiplied these two binomials, and then I've collected the terms that have 5 as a factor and factored it out. So a couple of easy algebraic steps are missing here. But the final result will be a times b plus 5 times the quantity at plus sb plus 5st. And now we are again in a position to use the inserting and deleting multiples of m lemma. Here is a multiple of 5 sitting inside a mod 5, so it can be deleted. We end up with a times b mod 5. Our proof is complete. We've now simplified the right-hand side and gotten the same thing as we did when we simplified the left-hand side. Okay, a few easy properties of homomorphisms. These were also properties of isomorphisms, and exactly the same arguments work here. F of the identity in G will always be the identity in H. And F preserves inverses. In other words, if you take an element A of G, then F of A inverse is matched with the inverse of F of A. There is an important set associated with each homomorphism. It's called the kernel. And the definition of the kernel, given a homomorphism F, the kernel of F is the set of elements of G that are matched with the identity in H. So the kernel of F will be a subset of G. It'll be those things in G that are matched with the identity in H. Okay, and a couple of facts. A fact about the kernel. If you have a homomorphism from G into H, then the kernel of F is a subgroup of G. And the range of F will be a subgroup of H. The fact that the kernel is a subgroup will come up in the exercises on homomorphisms. And as I said before, in almost all of our examples of homomorphisms, the range of F will be all of H. Okay, let's try finding a few kernels given homomorphisms, of given homomorphisms. So here is a homomorphism from Z20 to Z4, defined by f of x equals x mod 4. So we are working with Z20, not U20, and Z4, not U4. So the operations are plus sub 20 and plus sub 4. And the identities in both groups are the number 0, right? Because the operation is an addition. Okay, so remember Z20 consists of all the integers from 0 through 19. Z4 consists of all the integers 0 through 3. We want to find the kernel. Okay, by definition, it's the elements of Z20, of the domain of F, that are matched by F with the identity in Z4. So 0 is the identity in Z4. So if we replace F of A by its definition, this is the set of A's in Z20 for which A mod 4 is 0. So we're looking for numbers between 0 and 19 that give you a remainder of 0 when you divide by 4. The multiples of 4, right? 0, 4, 8, 12, and 16. Second example, U12, the function from U12 to U3 defined by f of x is x mod 3. Okay, this is a homomorphism. We're not going to prove it. We're assuming that the problem here is to find the kernel. Well, remember, U12 consists of the numbers between 1 and 11, which are relatively prime to 12. That would be 1, 5, 7, and 11. And similarly, U3 consists of the numbers 1 and 2. Okay, we work just like we did in the previous example. The kernel of f will be the elements of U12 that are matched with the identity in U3. Replacing f of a by what it's equal to, namely a mod 3, these are the set of elements in U12 for which a mod 3 is 1. The elements of U12 that give you a remainder of 1 when you divide by 3. Well, running through the elements of U12, the number 1 is one of those, the number 5 is not, the number 7 is, and the number 11 is not. The kernel of this homomorphism consists of the two numbers 1 and 7. Okay, let's try this third example. So now we're looking at the function f from the integers, the entire set of integers, into Z9, defined by f of x equals x mod 9. And we're using the usual operations on Z and Z9, namely plus and plus of 9. So the identity in Z9 in this case will be 0, because the operation is an addition. Okay, proceeding just like we did before, the kernel consists of those elements of Z that are matched with the identity in Z9. F of a is replaced by its definition, a mod 9. So we're looking for the integers a for which a mod 9 is 0. These are the integers divisible by 9. I could write it this way, 9k, as k runs through the integers. It's all integer multiples of 9. Okay, one final example. Why is this function not a homomorphism? The function from U12 defined by f of x equals x mod 5. Well, U12, as we saw before, consists of the numbers 1, 5, 7, and 11. And the operation on U12 is the usual, times sub 12. U5 consists of the numbers 1, 2, 3, and 4. The operation is times sub 5. So if we use the formula to calculate f of 5, we get f of 5 is 5 mod 5, which is 0. But this is not in U5. The function I've defined is not a function from U12 to U5, so cannot be a homomorphism. And now we're going to look at one final example. So we're looking at the function f from U53 to U73 defined by f of x equals x. This is not a homomorphism from the group U53 times sub 53 to the group U73, comma, time sub 73, and the question is, why? Is it not a homomorphism? Well, first note that 53 and 73 are both prime numbers, so that means that U53 consists of the positive integers from 1 through 52 inclusive. Every number between 1 and 52 is relatively prime to 53, since 53 is prime. And in a similar way, since 73 is a prime number, U sub 73 consists of the integers between 1 and 72 inclusive. The integers greater than or equal to 1 and less than 73. So that means that f of x equals x does define a function from U53 into U73. If you take one of the integers in U53, in other words, an integer from 1 to 52, apply the function f to it, you get that integer back again, and that will be an integer from between 1 and 72. So if we want to show that f is not a homomorphism, we're going to have to find two numbers, a and b, for which the homomorphism equation is false, for which f of a times sub 53b is not equal to f of a times sub 73 f of b. Okay, so here's a new slide where we have a little bit more room to work. The function is f of x equals x, and we're looking for two elements of U53 for which this inequality holds, for which f of a times sub 53b is not equal to f of a times sub 73 f of b. This is sort of a trial and error problem. So we're going to do a little exploring. So let's try a equals 5 and b equals 10. This is sort of a random choice of elements from U53. If this works, if for this choice of a and b this inequality holds, then we will be done. If the inequality doesn't hold, if it turns out that both sides of this equation are equal, for a equals 5 and b equals 10, then maybe we'll be able to decide why that happened, and from there find a choice of a and b that works. So let's calculate both sides of the equation. F of 5 times sub 5310. So 5 times sub 5310 is 5 times 10 mod 53. 5 times 10 is 50. 50 mod 53 is 50. So we are calculating f of 50 here. And since f of x is x for every x, f of 50 is 50. So the left-hand side of this equation with a equals 5 and b equals 10 is 50. And now we calculate the right-hand side. F of 5 times sub 73 f of 10. F of 5 is 5. F of 10 is 10. So this will be 5 times sub 73 10. 5 times sub 73 10 is 5 times 10 mod 73. That will be 50 mod 73, which is 50. It didn't work. But it's pretty clear from the example that if we choose a and b so that a times b is smaller than 53, then f of a times sub 53b is going to be a times b mod 53, which will be A times B, since A times B is less than 53. And f of A times B will be, according to the definition of f, A times B. And the other side of the equation, f of A times sub 73 f of B, will be A times sub 73b. According to the definition of times sub 73, this is A times B mod 73. Since A times B is less than 53, A times B mod 73 will be A times B. So choosing an A and B whose product is smaller than 53 doesn't work. So that gives me a route to follow. Let's try A equals 2 and B equals 27. What I was looking for here were two numbers whose product was 54. I want A times B to be greater than or equal to 53. So a product of 54, I'm hoping, will work. And now let's try calculating both sides of the equation again. F of 2 times sub 5327. 2 times sub 5327 is 54 mod 53, which is 1. So we're calculating f of 1 here, and f of 1 is 1. And working on the other side of the equation, f of 2 times sub 73 f of 27, f of 2 is 2, f of 27 is 27. So this should be not a 3, but should be 2 times sub 73 27. And this will be 2 times 27 mod 73. 2 times 27 is 54. Mod 73 is 54. I've got to correct the typo here. That 3 should be a 2. So A equals 2 and B equals 27 work. We've found an A and a B for which the two sides of the homomorphism equation are different. And we've shown that F is not a homomorphism.